All right. So here we are trying to review some of the problem in the chapter one quiz. Okay. So let's look at okay. Now the problem number two is very similar to the one I showed you during the lecture. I mean, the problem I showing you previously is that you have to show that there is a rational number or x such that this rational number or irrational number control any x, right? So we are given an x, you look for an irrational number which is
You guys
greater.
want to go together?
Hello? So that's the sample problem in the during the lecture, okay? So in the test problem, the number two is a slightly variation of this one. So question is, for every x, now you're looking for two irrational number, I1 and I2. I1 is smaller than x, I2 is greater than x. Okay, so this problem is very related. Now, my purpose of asking you to do this problem is because that I want you to use the same method as I show you during the lecture. I mean, this is the method. I mean, how to find Ix using the same method. Using this method means that you want to use the Archimedean properties to do this. Well, a number of students use the other method, does not follow exactly the instruction of the problem. So they use some other tools, but it's okay. But here I'm going to indicate how do you prove this using just the Archimedean properties. Okay, so a part of proof is already shown during the lecture. Okay, because that, for instance, suppose you want to find I2 controlling X. So you're based on Archimedean properties. And you can see that there is an integer m such that, so instead of using x, you are using x divided by square root 2. And I assuming that the square root 2 is irrational. Okay, so for x divided by square root 2, you know that there is a integer greater than this number. Okay, so this is guaranteed by Archimedean properties. Now, once I have this, and then I can simply multiply the square root 2 on both sides. Then you have x is less than m times square root 2. And now m is an integer and square root 2 is an irrational number. So the product must be an irrational number. So this means that I can just choose the I2 equals to m times the square root 2. Okay, that's an irrational number. So this procedure, this procedure actually showing you how to find I2. Now the question is I1. Now how do you find I1 is smaller than x? And you can proceed in a similar way. Now, when you find I2, so you look for, you apply Archimedean property to x divided by square root 2, right? Now here, to find I1, you apply the same property. You apply the Archimedean property to a different number. The number is supposed to be, actually you're using square root 2 divided by x instead of x divided by square root 2. Okay, just opposite. And then you can see based on Archimedean properties. And then you can find that the square root 2 divided by n, square root 2 divided by x is less than n. Okay, right? Based on the same reason. And then you actually, this time you multiply the x on both sides and divide by n on both sides. Okay, then you get the square root 2 divided by n is less than x. So that's why you can choose I1 equal to square root 2 divided by n, that's it. Then, of course, square root 2 divided by n is an irrational number because 1 over n is rational. It's a fraction, it's irrational. Any rational times irrational, you get irrational. So that's how you get I1. So that's the way I want you to present during the test. Well, if you use some other idea, use some other theorem, some student using like the density theorem, that's fine, okay? And but I also see some mistakes from some students the test. Okay, so I'm now reviewing this to give you another opportunity to understand this structural proof and understand these theorems. Okay, so this for number 2, which I'm trying to review with you. And now I also want to talk about number 4. Number 4 is connected to the nested cells property, right? Nested cells property. But it's not only using the nested cells property, but also in the connection with the corollary. So combining nested cells property and the corollary, what we can conclude is that if you have a sequence of non-empty closed cells, which is nested, then all the intersection of all these closed interval will be exactly equal to the interval C in the eta. Okay, so that's the result given by nested cells property. Now, here, what we are trying to show in the number 4, the condition is that suppose the AN, the interval IN, the length of interval IN approach to 0. Of course, I didn't say that. I only saying that this length of IN basically is BN minus AN is less than any epsilon. Okay, as long as N is large enough. So that's basically saying that the length of IN actually approach to 0. Now, with this condition, I want you to show that the intersection consists only one point. Okay, you cannot consider interval like this. So in other words, I want you to show that C is equal to eta. Okay, so that's number 4. Now, how do you do that? So obviously, you can do this use contradiction method. Okay, or you can use direct method, and we'll see. Okay, which method is more convenient. Okay, all right. So this is one way to do that. Now, you based on your assumption, you're saying that Bn minus An is less than epsilon for n large enough, right? So we're going to show that this will imply that C equal to n. Then we're finishing the proof. Okay, now how you can reach this? So we first notice that this interval C and eta is equals to all the intersection. So this is actually from what? This is actually from the nested cells property and corollary, right? So this means that this interval is actually contained in Rn and Bn for any n. Okay, so because they are in the intersections. So this indicates that the length of the left side, that eta minus C, that's the length of the left side, must be less than the length of any interval in the sequence, which is Bn minus An. Okay. But I know that Bn minus An is less than epsilon for n large enough. So this indicates that eta minus C, okay, is less than epsilon for any epsilon, okay, no matter how small epsilon is. So this will indicate that there's only one possibility. That's eta equal to C. That's how we prove this result. Now, if you look at this argument, you can see this is a direct proof. We're not using the method of contradiction. But however, the same argument can be reformulated and to write this proof in a contradiction way. Okay, but it's depending on how you want to express this. Okay, so this is so if you really see the point of this problem, you can write a very short proof without a long explanation. It's just like that. So I recommend you to rethink about this result. Okay, and also you think about, now here I'm presenting the direct proof. Now how do you think about you can present the indirect proof, like a contradiction proof? All right. So this is what I want to review with you about the chapter 1 quiz. So do you have any questions? If no questions, then I think we should continue on the previous lecture. Okay. So let me let me stop sharing this one. Hold on just a second. It's not right here. Okay, here it is here. Okay, so now let's begin with our new lecture. Okay, now remember last time we actually I show you I asked you to 2 problems. I don't know whether you have finished that yet. So I want to review this problem with you because these problems are actually like, especially the first one, they are just a very simple problem. They are related to the Math 415. Okay, and so I'll just show you some of the steps and you can look at by yourself. And I don't think you'll have any problem with this but however, the numbers like the expression 7n over 4n plus 11, so this number may create some, computations with some number. Okay, so I don't see there will be a problem with the number 1. All right, so let's look at the number 2. Number 2 is related to the last example in the previous lecture about a limit of n to the 1 where n goes to 1. Now this time, I want you to show that 1 plus 2n to the 1 where n also goes to 1. So the n is replaced by 1 plus 2n, okay, in the first place. And so this is a required new proof, but it's followed from the same argument. So I think you have practiced, okay? And I want to, and now we are work together to go through these steps. Now follow exactly the same thinking. Now you notice that the 1 plus 2n, okay, to the 1 where n is something is greater than 1. Okay, so therefore you can write this expression into 1 plus bn. And thinking about bn is another sequence. Bn is greater than 0, obviously, because the whole expression is greater than 1. Okay, and then we follow the same step. I begin to take n's power on both sides. So you can remove the power 1 over n. So left-hand side will become 1 plus 2n. The right side is 1 plus bn to n's power. Now, this is the place you have to think more carefully. Okay. Now, previously, if you remember in the last proof, you know that we began to use the binomial expansion, right? Now, using binomial expansion, actually previously, you are using the third term. That's the term with n and n minus 1, okay? So therefore, you can see using this term, this means that I have 2n there. So one of the n can be canceled with the n on the left side, right? So that's the purpose. Now this time, because there's a 1 on the left side, so it's more convenient that you're not just using the third term, you're also including the first term. You include the first 1 there. So therefore, you can see what we're having here is 1 plus bn to the n's power is greater or equal than 1 plus n to n minus 1 divided by 2 than bn squared. Okay, so doing this, you can see that the 1 can be canceled. Okay, then it's easier for you to solve the next inequality. Now, once 1 canceled, the left side 2n. the right side is n times n minus 1 and so on, right? So you can cancel another thing that's n. You can cancel another thing that's n easily. Then you will see that you can rewrite this inequality. So you get a control of Bn. So Bn is less or equal than the square root, okay? Square root 4 over n minus 1. That's 2 over square root n minus 1. So you get a control of Bn. So what you need to show next is to show that the right side 2 over square root n minus 1 will goes to 0. Okay, now this is easy, right? Because you have an n in the denominator, it has to goes to 0. So, but however, you still need to using the epsilon k argument to do that. So for every given epsilon, you choose k, okay? Now here, I skip some writing, some analysis steps. Okay, actually you have to choose k is greater than 2 over epsilon square plus 1. And when this happens, then you can see when n greater than k, you have an n is also greater than this. And this n will give you that inequality, that Bn things, okay? Now you will get a 2 over square root n minus 1 less than epsilon. So this will imply that by the above inequality, this will imply that Bn is less than epsilon. And then you can go to the final inequality. So that's 1 plus 2n to n minus 1, which is equal to 1 plus Bn minus 1, which is equal to Bn, that's epsilon. So that's how we conclude the proof for this problem, okay? So all these examples are important. But they are the practical, I mean the example with actual sequences, okay? But here in this chapter, we're not just want to handle these actual sequences, how to use the epsilon argument to prove the limit, but also we want to establish the general theory about the limit. Okay, so this is we have to move further to establish a theory. Okay, all right. So let's see what we can do today. I'm trying to show you two things. The first things we want to prove a theorem is called the uniqueness of limit. So that's part of the limit theory. Okay, when you talk about limit is a general concept, it's an abstract concept. Okay, so this limit carries certain properties. So one of the important properties is called the uniqueness of the limit. Now, what does uniqueness mean? So it is very simple, actually. So it's saying that a sequence, suppose you have a sequence, okay, in R, then this sequence can have at most one limit. So when we have a sequence, I don't know whether the sequence carries a limit or not. Maybe the sequence has no limit. So that's one situation. And maybe the sequence carries some limit. So that's another case, right? But in the second case, if the sequence has a limit, then the sequence can only have one limit. The sequence cannot have two different limits. Okay, that's the first theorem. Now, this is a very simple fact. If you think about this, if your sequence goes to some number, fixed number, then obviously the sequence cannot at the same time goes to a different number. That's impossible. Okay, so that's the things we want to justify first. It looks like simple, but however, we want to in this class we want to prove everything using the epsilon language. Okay, that's the official language you can use in proving anything related to the limit. Okay, you cannot describe what you think was going on. That's not a proof. Okay. Okay, so in this proof, the correct method is to use the method of contradiction. So using method of contradiction basically means that you just assume that the sequence carries two limits. Now suppose you get Xn, okay, is a sequence of real number that converges two distinct limits, x and y. Okay, and then from here, we are going to get a contradiction. Now, here is a technical word after that. I say that choose epsilon less than 1/2 square root x minus y. What does it mean? I will explain using a graph, okay? Now, the proof of this is, now thinking about it, the idea is very simple. You think about this case on the number line, Okay, you have x and y. Okay, you have x and y are considered as two distinct limits. Okay, all from the sigma xn. And then I'm going to create two intervals surrounding, centered at x and y, so that these two intervals are not, these two intervals has no intersection, basically. They are separate. So obviously, I can reach this by choosing the radius of the interval equals to is something less than half of the x minus y. Okay, I can certainly do that, right? As long as epsilon is less than 1/2 of the distance between x and y, I'm using this epsilon to create a first interval centered at x, and also using the same epsilon create another interval centered at y. Now these two intervals, they are open interval. Now even though the epsilon can equals to the half of the distance, however, because they're equal, so these two interval does not carry any common points. Okay, so that's the first step I want. So when we go through this proof, I want to choose these two intervals. Now this two interval is going to create a contradiction. Think about it. Now if an xn goes to x, right? So this means eventually the xn will be very, very close to x. So this means xn will be in the first interval. And same time, if xn goes to y, so this means that when n large enough, then xn will be in the y interval. So now you're creating some contradiction situation. The same xn will be in the first interval, in the x interval, and the same time in the y interval. Then this will be contradicted to each other, right? So that's the proof. That's the idea of proof. But however, we cannot just write on proof by describe this using a paragraph by saying what I said just moments ago. That's not a proof. So we have used the definition of xn and work on each step one to one step, one by one, in order to reach a contradiction. The contradiction is that basically xn will be in the x interval at the same time at the y interval. That's all contradiction. Okay, so we'll see how we can make this happen. So all right. Okay, so let's see. Proof continues. Okay. So here we begin to use the definition of limits. Okay. Now I'm saying that xn goes to x. Okay. Xn goes to x. Okay. So what does it mean? This means about epsilon definition. So there is a integer k in n. Now this time I label this k by k1 because next step I want to also work for the next limit. I mean xn also goes to y. So I'm going to indicate this k, which is related to the x, to be the k1, such that if n greater than k1, then the distance between xn and x is less than epsilon to make this happen. So what does this tell us? This basically tells us that if n is greater than k1, then the term xn will be in the x interval because the distance to the center is less than epsilon. Okay. Now we continue because I know that the xn also assumed to be converged to y. So based on this assumption, the new assumption, so you can see there's a second integer. Now I denote by k2, such that when n is greater than k2, then xn minus y to the next center, y, is also less than epsilon. Okay. Now these two things should contradict to each other. So if you imagine the picture there, so the first inequality tells you that xn is in the x interval and xn at the same time now in the y interval, right? So these two, how can this happen? There will be clear contradiction. Okay. But mathematically, to reveal this contradiction, to show this contradiction, we have to do a few steps. Okay. Now, what we can do first is that you can see, so when n greater than k1, you have first inequality. Then n greater than k2, you have the second inequality. Okay, but k1 may not exactly equal to k2. Okay, so I want to choose n large enough so that both happens. So we can do this by choosing n is greater than maximum k1, k2. So when n is greater than maximum k1, k2, obviously both inequalities should hold. Okay, now you can see that how do I see the contradiction here? Now here I have to do some using some inequality to show this and to show the contradiction. Okay, so what do I do is I use triangle inequality here. The triangle inequality I'm using is that the absolute value a plus b is less than absolute value a plus absolute value b. So this is the triangle inequality. Pretty soon in the next theorem, we're going to see a variation of this triangle inequality. Okay. Now normally this is called first kind inequality. The other kind is called a second kind, but I will show this later. Now what we can do use this triangle inequality to get contradiction. So that's the idea. Now I look at the distance x minus y. Okay. I want to estimate this distance in terms of x n. So we can do that by insert the term inside the absolute value. So I insert x minus xn, then plus xn. So minus xn cancel with plus xn. So therefore, nothing changed. So therefore, x minus y absolute value equal to the second term. And now in the second term, I view x minus n equal a in the triangle inequality, and xn minus y to be the b in the triangle inequality. Then you apply the triangle inequality, you will easily see that the xn minus x absolute value plus absolute value xn minus y, right? So the right side two term now controlling x minus y. Now that's the key step you should use in order to show the contradiction. Why? Because I know exactly how to control xn minus x and xn minus y. Because this is the next step. I know that the both terms are less than epsilon by given the previous condition, right? 2 epsilon. Okay, then I know that epsilon is less than or equals to 1/2 x minus y. So I can replace this epsilon by 1/2 x minus y. And then 2 and 1/2 canceled. You'll get exactly x minus y. Now this will give you a contradiction already. Why? Because you look at from the left side to the right side. Okay, very left side to the very right side. In the middle, you have equal sign, right? And you have less or equal to sign, but also you have strict less sign. Okay, so you're putting this together, okay, you can see that this means that absolute value x minus y less than absolute value x minus y. And this is a contradiction because for the same number, okay, you can't have said, like say the number is a, you can see a is strictly less than a. No, there's no such number. Okay, so this contradicts to the common sense. Okay, so this contradiction shows that the previous assumption is wrong. Our original assumption is wrong. Okay, so this shows that it's in the proof. Okay, now this is the first proof. You can see that how we use epsilon language and this tool to prove some general theory. Okay, now this is what you want to learn in this chapter. I will help you to build up this ability. Okay, now in order to build up this ability, you have to first, the one step is you have to study these proofs. Okay, study these model proofs very closely, and then you work on some similar problems, and this is how you get familiar with these tools. All right. Okay. Any questions? Okay. That's good. There's no questions. So then I'm going to continue on the next result. Now today I'm going to only show you 2 results. Okay, 2 proofs, 2 theorems. Then I'm going to indicate some of the homework you need to work on. Now the second theorem, 2.3. This theorem is still another general theory about the limit. It's called the boundedness of convergent sequence. Now previously we talked about the arbitrary sequence, but mostly we're talking about convergent sequence. So that means any sequence can have at most one limit, right? But especially for the convergent sequence, that convergence sequence can only have one unique limit. So that's called a uniqueness theorem. Now here we're also dealing with, we're not dealing with general sequence, we're dealing with convergent sequence. And so this result saying that actually any convergent sequence, okay, it's not, okay, previous result tell us any convergent sequence can only have one limit. Okay, now this theorem tells us any convergent sequence is also a bounded sequence. It's a bounded sequence. So what is mean by a sequence bounded sequence? This means that there is a positive number, so that this positive number is controlled every turn in the sequence. So this means the whole sequence must be inside some finite interval. So this mean by what I mean by sequence is bounded. Okay, so here we are going to prove this, and this proof is very different from the previous proof. Our previous proof using contradiction method. Okay, but this proof we're trying to use a direct method. But no matter what method we're going to use, you're going to see that we use the same tool using the epsilon argument as a tool. Okay, now we have a bounded sequence, right? We have a convergent sequence. Okay, now every time in the assumption you know that a sequence is convergent, you always want to think about it, how to apply the definition of convergent sequence. That means you think about the epsilon. Okay, you think about epsilon. How do you use this epsilon? Because every time you have a convergent sequence, then the limit exists. So therefore, you can apply the epsilon argument, right, to describe limit. But epsilon can be arbitrary. Okay, so therefore you have many freedom to use this epsilon. Okay, so now in this case, let's assume that the limit of xn equal to x. Okay, this is our assumption, right? And then you can use epsilon argument. And now this time I'm just use, I'm not going to use arbitrary epsilon, okay? I just use epsilon equal 1. Now when you use epsilon equal to 1, so everything must be whole in the definition, right? So if I choose epsilon equal to 1, so this is what we're going to get. So based on this epsilon, there is a k in n, such that when n greater than k, then xn minus x less than 1. Okay, so I just use, now it is not necessary for you to choose exactly epsilon equal 1. You can choose epsilon equal 2 or epsilon equals to 3, and then actually assign you choose any fixed epsilon. Okay, then you're going to reach the same goal. But for the convenience, we just use epsilon equal 1. Okay, so by choosing epsilon equal 1, we're going to get that obviously xn minus x absolute value is less than 1, when n is greater than k, right? So this is a consequence of the limit definition. Now from here, I'm going to show that this sequence must be a convergent, must be a bounded sequence, okay? Now how are you going to see it? So, so from this inequality, so we're going to see that the next step, we're going to see that, okay, I will be able to get another new inequality it's different from the previous one. That's absolute value xn minus x absolute value is that one. So this second inequality is a consequence of the previous inequality. Now why? And this again follows from the triangle inequality, but in a different directions. Okay, so here is the new inequality I'm going to show you, because so this is what we call the second kind of triangle inequality. Okay, it's absolute value a minus absolute value b is always less or equal than a minus b absolute value. We are using this inequality here. Okay, now the proof of this new inequality is very simple. I can use the previous triangle inequality to prove it. The argument is that you start with absolute value of a. Okay, so you rewrite this a in terms of absolute value of a minus b plus b. So basically you're inserting b there. Minus b and plus b canceled, basically. Okay, so nothing changed, right? And then you use the triangle inequality to the second term, a minus b plus b, and treating the a minus b as one thing, b the second thing using the triangle inequality, you'll get an absolute value a minus b plus absolute value of b, right? Using the standard triangle inequality, you can get this. And then you subtract the absolute value b on both sides, you'll get the new inequality, which is absolute value a minus absolute value b is less or equal than a minus b. So this is the inequality we're going to use. Well, this is a very important inequality. It's a variation of the standard triangle inequality, okay? And sometimes we call it the second kind of triangle inequality. And you're going to see this kind of application later in other proofs. But anyway, so return to our proof. You can see our first inequality is showing that absolute value xn minus x is less than 1. So this inequality will immediately give you absolute value xn minus absolute value x is less than 1, right? Now, once I have this second inequality, and then you can see I can add absolute value x on both sides to get the xn absolute value is less than x absolute value plus 1. Now, this is very significant. So look at the third inequality here. The third inequality tell us a lot of things. So this third inequality simply tells us that every term in the sequence, okay, for every term in the sequence, xn, the absolute value is controlled by a fixed number. Now, what is this fixed number? This fixed number is x absolute value plus 1, because x is fixed. It's independent of n. So this simply saying that the term xn absolute value in the sequence is always less than this fixed number. This already showing you this term is bounded. The term is bounded by x absolute value plus 1. So we almost reached to the conclusion that the sequence is bounded, right? Okay, but however, there's a gap. The gap is that in order to have this, you have a condition. The condition is x is n is greater than k. When n is greater than k, you will have this. So when n is greater than k, every term after that are bounded, controlled by absolute value of x plus 1. Okay. Now the question is, what about the previous terms, like the x1, x2 up to the x capital K? How about these things? Are bounded or not? Certainly they're bounded because they are only finite number of terms. So I can increase that number. I increase the number x absolute value plus 1 to increase this number to control the first few finite terms. Okay. So that the whole sequence will be bounded, okay? So the simplest way to include this term is to redefine a number, okay? The number is maximum, okay? The maximum of x1 to xk with absolute value sign. So once I include this x1 to xk, you can see this number is big enough to control the first k terms. Then I also include the absolute value x plus 1. So the last number control the rest of the term after xk. So this may be a big number, but this number is a fixed number because it does not depend on n, right? It only depends on k. And k depends on epsilon, which is equal to 1. Okay, so I just use this big number, huge number. So this huge number controls everything, every term in the sequence. Okay, so so this is actually reached the conclusion. I mean, you look at this situation. So you can see, so the whole sequence is inside interval from the left endpoint is minus absolute value x, then minus 1. The right endpoint of interval is x absolute value plus 1. So I denote these two endpoint by the red, using red color. Okay, so the whole, so you can see when n greater than k, xn will automatically inside this red interval. Okay, and of course there are some other terms outside of this interval. Then I increase the radius of the intervals. Okay, by inserting x1 to xk inside. And then you can see the whole interval will include everything. This simply shows that all the terms in the sequence are inside a big interval. So therefore, they're bounded. Okay. So that's the proof of this second theorem, 2-point straight. Okay. Any questions? Okay. I hope I present this clearly. Okay, you can get these ideas. And now, before I move on to the next step, I want to assign a few homework, some homework. Okay. So the homework is number 4 and number 5. Number 4 and number 5. Okay. Now, what you need to do today is you review the proofs you learned from the class, and then you begin work on this 4 and 5. Now, here I'm going to give you some hint. Okay. Now, I'll tell you that number 4 is very simple. Number 5, you need to think about it. And next time, before we go on to the next new things, I'm going to review this homework with you. Okay. So let's think about number 4. So number 4 is basically saying that if your sequence, okay, carry a limit 1, and then you can, so what we really want to do is that, so there's maybe some question. Okay, some students have a question regarding the okay, no problems. Okay, good. All right, so this is very fun stuff. Okay, working on epsilon arguments. Okay, now here is that you can think about this. Xn goes 1. Xn goes 1. So you can see that then you can see when n large enough, the xn will be very, very close to 1. Now, when x is very, very close to 1, the xn has to be greater than 0.99, obviously. Okay, right? If the xn is very close to 1. Now, how you can do this? How you can justify this? You justify this using a special epsilon together with the definition. Okay. Now, so you look at the distance between 0.11 or 0.99 to 1. So the distance is 0.01. So now, intentionally, you want to create epsilon equal to 0.01. Okay. Now this will help us. Why? Because hold on just a second. All right. Okay, you think about this way. Okay, so you're using epsilon equal to 0.01. Okay, you create an interval surrounding 1. So left endpoint is 0.99. The right endpoint is obviously 0.01, 1.01, right? 1.01. So this interval. So you can see that. So this means by you choose epsilon equal to 0.01. So you create an interval like this surrounding 1. Okay, and then you can see based on the epsilon argument, then when n large enough, xn will be inside this interval. Has to be inside this interval, and this will indicate that the xn obviously will be greater than the left endpoint. That's xn is greater than 0.99. That's it. That's the ideal proof. Okay. Okay. So, well, of course, you can choose a smaller epsilon, but it's not necessary, right? In order for the purpose of proof, you only need to choose some simple. I mean, epsilon 0.101 is sufficient. But again, you cannot just describe this using a graph or just explain this by a paragraph. You have to use mathematical symbols to do this. So using epsilon equals to 0.01, okay, you can see that by definition, you can see that xn minus 1 will be less than 0.01 eventually when n large enough, right? And this inequality, now here is something new maybe. This inequality with absolute value sign can be expressed by using two inequality without absolute value. So basically, you see, take off the inequality, the absolute value sign, you immediately get xn minus 1 should be less than 0.01, right? But on the left side, it has to be greater than minus epsilon, which is minus 0.1. Okay. So from the inequality you get from the definition, epsilon definition, now you can remove this absolute value sign, okay, to reach an equivalent inequality like this. And a part of this inequality will be sufficient to prove our result, because now you're adding one to both each side of this inequality. On the left side, you're adding 1, you are becoming 0.99, right? So you're getting 0.99 smaller than xn. On the right side, you're adding 1, you get 1.01. Okay, xn is less than 1.01. Okay, but only half of this inequality is relevant to this problem. We only use the left side of the inequality, the xn greater than 0.99. That's it. That's what shows the result. Well, the same procedure will show you that when n large enough, xn should be less than 1.01. Okay, you get a byproduct. All right. So this is a model problem. Okay, and you can work. I mean, use this same argument work on different kind of problems. Okay, as long as you have a limit. So this means that xn will be very close to the limit. Okay, so therefore xn will carry a certain property, maybe less than some given number or smaller than some given number when n large enough, as long as this number is not equal to the limit. Okay, so that's the number 4. Now number 5, I'm not going to provide the full detail. I want you to think about it, and next time I'm going to come back to it. Okay, so let's look at number 5. Number 5 is that you have an xn. Okay, it's a positive sequence. So this means every xn is positive. It's not negative. It's positive. Okay. In R, with a limit xn equal to x. So what we want to show is that, like, the limit itself has to be non-negative. Now the limit itself may not be strictly positive. Okay, there's a lot of examples like that. Suppose, like, say, think about the xn equal 1 over n. 1 over n is positive, but 1 over n will go to 0. It does not approach to something strictly positive. Okay, so the best you can show is that you want to show that x has to be greater than or equal to 0. And in this case, now how you can do that? In this case, it's convenient. So that's a recommended approach. The convenient to use the method of contradiction. Okay, you assume that x is less than 0 and trying to get a contradiction. Okay, now I can continue with a graph. So that's the situation. 0 is there, now, assuming x on the left side, strictly less than 0. Okay, and then here you want to get a contradiction. The assumption is every 10xn is on the right side. Now the limit on the left side. Now if you can show that some of the term will also be on the left side, that will contradict to the assumption. So how do you do this? The easy way to do this is you observe that between x and 0, okay, there's a gap, right? You try to choose an epsilon, okay, it's smaller than this gap. Okay, so then you can see that you apply the epsilon argument. When n is greater than a certain number, then you can see every 10 will be in that epsilon neighborhood of x. So once the term in that interval center at x, the xn will be on the left side of 0. That will create a contradiction. So that's the way. And you're trying to write this out by yourself. Now, I want to say that every time I give you the homework problem and I give you some hint, and afterwards I give you a review about giving the full solution, it doesn't mean that you don't have to do the homework. So by doing this homework, practice by yourself is extremely important. Okay, you have to do this by yourself, even though you have problem. So you have to go through this process. Otherwise, you are unable. You won't be able to create your ability of being how to apply these tools. Okay. Okay. So this is the homework problem 4 and 5, and for today's lecture. and I want to examine this with you next time. Especially on the next time we're going to examine with the number 5, okay? And then there's a few other things I want to go through with you. And the number of 2.4 is a small problem. It's just what we call non-convergence. So the theorem, what I mean by non-convergence, this means how did you say a sequence does not converge to something? Does not converge to something. That means I'm talking about negation of the epsilon definition. Okay. So this says that suppose you have sequence xn, be a sequence, okay? You have x. Now, what does it mean? Limit xn is not equal to x. What does it mean? Okay. Now, limit xn equal to x, there's a definition, right? Now, this is a negation of that definition. So in the Math 415, we learn how to negate things, right? We negate the universal quantifier and also the existential quantifier. We know how to do that. So if you do this, so you will get the result, okay? So the limit xn not equal to x, this means the following. There must be a special epsilon. We denote by epsilon greater than 0, such that for each k, there exists n greater than k, such that xn minus x greater or equal than epsilon naught. So that's the way to express the situation where the limit xn is not equal to x. So there must be, there is a special epsilon naught. Now, what kind of epsilon naught is? It not provide this information. It's not provided by the theorem. The theorem only says that there must be exist such things to make this happen. Okay, and this proof I don't have to go through this proof because this is a negation of the statement in the definition of limit. So you can review the negation of quantify by yourself and negate it. Once you negate it in the logic level, you can re-express this using a sentence, and this is the sentence you're going to get. Okay, so that's the number 2.5. Well, we're going to use this later, okay, to in some situation. Another thing is I'm going to indicate that, so here we're talking about limit is in the first one-dimensional Euclidean space. Now you can extend the limit concept in the multi-dimensional Euclidean space, okay? You can talk about xn, they are not just a number, they are points in RP. So being a point is xn carry components, like there's a p-dimensional. So that's the xn, each xn can have p components, okay? So I denote the components about 1 to up to p. So this means that if you have a sequence of points, and then you basically, for each component, you have a sequence of number. Like the first component is x1n, n varies. So the first component consists of numbers of sequence, a sequence of numbers. The second component consists of another sequence of number. Okay, every component consists of a sequence of number. You have p sequence of numbers associated with a sequence of points, right? Okay, and then you can use the same way to define the limits. Now, suppose you have a point x. X is another point not involved with sequence, okay? What should we say x is a limit of this sequence of point? So this means that the same definition, okay, except that in the last inequality, you use the distance formula to replace the absolute value sign. Okay, so this distance represents Euclidean distance defined by this. So the distance is defined by the distance between the components, the square, the sum of square, then take the square root. We're going to have more to say about this, about Euclidean distance later. But here, the Euclidean distance, using Euclidean distance, you can actually define the limit. Okay, so if you do that, you can have the following theorem. The theorem, we're not going to give a complete proof of the theorem, and I'll just mention it, okay? Yeah, and our focus in this class is a one-dimensional case. So it's saying that the sequence xn in Rp, a sequence of points, okay, it converges to a point x, which carries p components, of course. If only if for every k, the sequence xkn, the sequence of numbers associated with that components, right? In R, so the sequence of components is a sequence of number in R, convert to the corresponding components xk in the limit points. Okay, so this is what I mean by that. So you have a sequence of points. You have each component, right? Each coordinate, so you can say each coordinate will correspondingly converge to the coordinates in the limit points. That's the theorem. Okay, so if you have a limit of sequence of points, and for each coordinate, this will happen. Now, if for each coordinate this happens, then this will also imply that the limit of sequence point will converge into the given point. Okay. Now, if you want to learn more about this proof, which I not intend to give in this in my lecture, and you can look at the lecture notes. Lecture notes consist of the detailed proof. Okay. Okay. So, any questions? This is all I have to say today. So I wish you to review these proofs and work on the homework problems. And then we're going to see you trying to review a part of it next time. And before we move on, the next thing is about the subsequence and combinations. But we're not talking about this today. All right. Okay, that's it for today. All right. Okay, thank you.